Hey guys, in this video we're going to talk about Chapter 3, Section 1, Intro to the Family of Quadratic Functions. We're going to talk about what that means algebraically and graphically. In particular, we're going to talk about standard form, factored form, and graphs as well as equations. Okay, so what is a quadratic function? Well, a quadratic function, first and foremost, is a function. It has inputs. The x variable typically is used as our input variable, and we can get an output. So just like linear functions, a quadratic function is in fact a function. Algebraically, what does it look like? Well, one way of looking at a quadratic function is to view it like this. Okay, so we have f of x equals ax squared plus bx plus c. Now, as I mentioned, typically x is our input variable. So we're gonna be inputting a number or maybe some other expression into that equation, and we're gonna be getting something out, right? That's our f of x. Okay, so a quadratic function takes this form, and this form is called standard form. Okay, and so typically, we'll either use f of x, y, g of x. Sometimes we like to use t as our input variable for quadratics, and that'll be obvious why we do that later on in the lecture. But the idea here is that a, b, and c are all numbers, okay? So we call this standard form. And so that's what it looks like algebraically. It looks like this, where a, b, and c are numbers. And what does it look like graphically? Well, graphically, it looks U-shaped, and it can be either a U that's right side up, so concave up, or it can be a U that's concave down. So that's what a quadratic function is. It's U-shaped. Sometimes we call these graphs. Maybe this is a little note here. So the graphs can be called, the graphs of quadratics are also called parabolas. Sometimes that word is used. All right, so let's take a look at some examples. Now, Desmos is our best friend. We use it to graph. It's very good at doing that. And so I have two examples that I just kind of made up. And the first example is this quadratic function. F of x equals 3x squared minus 2x plus 1. And notice that it takes this form, right? There's an output, and there's three numbers that represent a, b, and c. And there's an x squared, and there's an x. So in this case, a would equal 3 because it's attached to x squared, just like in this form right here. B would equal negative 2, right, because it's attached to the x. And our constant is c, and that constant number is just positive 1. So that's a quadratic function. You can make up infinitely many quadratic functions however you want. So you could say a is 100, b is negative 82, c is 3 million. That would be quadratic. As long as you have that x squared in there, it's quadratic, as long as you have the x squared. You actually, the b value, so this value right here could be 0. That's a possibility. But you have to have this x squared term in there for it to be quadratic. But you don't need an x term. You just need an x squared for it to be considered quadratic. Okay, so, we just did this a, b, and c. A was 3, b was negative 2, and c was 1. And this is what it would look like if you were to graph it in Desmos. So if you were to put that equation in Desmos, you'd get something that looks like this, and it's a U-shaped, right? So it looks just like how we would expect it to look. Now, here's another example I just made up. I made up a, b, and c. So again, a is the number attached. Based on our standard form, a is the number attached to x squared. So what's attached to x squared is negative 5, so that's a. B is going to be this number attached to x, so that's positive 6. And c is that constant number, negative 3. So that's quadratic because, again, highest power of the variable is 2. And if we put this function into Desmos, we're going to get an upside down U. We're going to get something that's concave down. And we'll talk about so maybe this would be an exercise. What do you think is the difference between these two quadratics that makes this one concave down versus this one being concave up? What about the formula is causing this one to go down? What do you think? We'll get to that answer in just a minute. And here it is. Okay, so here's two important ideas about standard form. So depending on how you look at these equations, you can gather different sorts of information about what the graph looks like. Now, when you're in standard form, which is that f of x equals ax squared plus bx plus c, I'll write it over here. So y or f of x, doesn't matter which one you use. Ax squared plus bx plus c. That's standard form. It gives us two really big pieces of information, okay? The first piece of information is what a tells us, okay? That number a is going to tell us whether it's concave up or concave down. And that all depends on if a is positive or negative. Doesn't matter about fractions, doesn't matter about decimals. It's very simple. Is it positive? If it's positive, it's concave up. Okay, smiley face. If that a is negative, it's concave down. Frowny face. So if we go back to this slide, well, look, right here, a was positive, so we got a concave up graph. Here, a is negative. We get a concave down graph. Simple as that. So that's one nice piece of information that standard form gives us without even looking at the graph, okay? So that's the first piece of information. The second piece of information is this guy right here, is c, okay? That constant term at the end, that constant number. That gives us the y-intercept, okay? And the y-intercept is where the graph crosses the y-axis. So if you notice, let's go back to our examples here. Here, our c is 1, and we can see indeed on our picture right here, we can see that the y-intercept is 1. That's where it crosses the y-axis at y equals 1. And in a similar way, here our y-intercept is -3, so we expect this thing to cross the y-axis at -3, and it does. And it does. So that's the two important things that standard form gives us. All right, so let's put these ideas into practice. So we can tell if a quadratic is concave up or down, so happy or sad face. And we can also tell what the y-intercept is just from the standard form, right? So if we are in standard form, we can conclude these two things, whether it's concave up or down, and also what the y-intercept is. So let's look at number 1. First of all, is it in standard form? Well, yes, it is. We have an x squared is our highest term, or our highest variable term here. And we have an a, we have a b, and we have a c, right? So this is a, b, and c. Now, remember, to determine whether it's concave up or down only depends on a, and whether it's positive or negative. So since a is positive for number 1, a is 2, that means that it's going to be concave up, and since c is equal to 1, that's going to tell me that my y-intercept is 1. So that's what we know about this thing. We know that it's going to pass through 1, and it's going to be concave up. So let's go ahead and maybe do a little sketch of what that might look like. I don't know. It might look something like this, just based on the information that we have. So this is our y-intercept of 1. And remember, with y-intercepts, x is always 0. So when x is 0, y is 1. So we know that, and we know that it has this U shape, and that's kind of all we can infer at this point. Okay, What about number 2? All right, so are we in standard form? Well, yeah, we are. We have an x squared, we have an x, we have a constant number. Here our a is that number attached to x squared, which is negative 3. Our b is positive 3, and our c is 5. So in this case, a is negative 3. So since a is negative, this is going to be concave down. So it's going to look something like that. And that's what a tells us. Now our c is going to be positive 5, which means that's where it crosses the y-axis. Oops, sorry. So the y-intercept is 5. So we don't know a ton about this yet. And you know, what you could figure out, you could figure out some other points on this thing by just plugging in, just like we did in the first section, when we plugged in, we didn't do that in section 1, but when you learned this in intermediate algebra, what you did with functions is you plugged in numbers into x and you got out a y value. So you can figure out points on the curve that way. And we're going to do more of that in the next section when we talk about vertex form. But for now, we could get a rough picture. We know the shape of it. It's concave down. We know that it passes through y equals 5. And we also, and that's really all we know, basically. So, you know, maybe it looks, I don't know, let's see. Maybe it looks something like this. Maybe it looks something like that. And this is y equals 5, x equals 0. That's our y-intercept there. All right, let's look at number 3. Are we in standard form? Well, yeah, but we have things rearranged a little bit. So if it helps you, write the highest power term first. So I'm just going to rewrite this so it looks just like standard form up here. And standard form has the x squared term first. Okay, so the x squared term is a positive 5. In this case, our variable is t. So it's going to be 5t squared comes first, followed by a positive 2t. Now the positive isn't written there, but it's implied to be there because there's no negative in front of it. And the negative 1 is going to hang out in the back. All right, now we're in standard form. Okay, so we have a, we have b, and we have c. And a is positive 5. Now since a is positive 5, that means it's concave up. It's going to look like that. And our c is going to be negative 1, which means that our y-intercept, where it crosses the y-axis, is negative 1. Okay? All right, so that is standard. That's what standard form tells you graphically. All right, what about something like this? So is this in standard form? Is this one in standard form? Well, no, it's not, right? Standard form looks like this. ax squared plus bx plus c. Simple as that. Replace a, b, and c with numbers. This doesn't look like that. We don't even see a squared term. However, we can manipulate this thing, right, using our algebra skills to put it in standard form. Right now, it's not there, but what we can do is we can FOIL, right, because I have something in parentheses times something over here, right? There's no symbol in between these things, so that means multiply. So we're gonna FOIL, and then we can manipulate it to look like this. Okay? So FOIL, we're gonna do first, which is x times 2x. So first, x times 2x is 2x squared. Our outer is going to be, one second. Okay, our outer is going to be, let's see, we have x is on the outside there, and negative 3 is on the outside here. So x times negative 3 is a negative 3x. Our inner is positive 8 times 2x. So positive 8 times 2x is going to be a positive 16x. And finally, last is going to be positive 8 times a negative 3. So positive 8 times a negative 3 is a negative 24. And at this point, what we can do is we can combine like terms. So the only like terms we have are the x terms. So let me go ahead and just combine these. We have y equals 2x squared. Negative 3 and a positive 16x is going to give us a positive 13x when I combine these. And then at this point, we are in standard form. Okay, right? Because we have ax squared, bx, c. It looks just like this. So at this point, we can identify our a and our c and our b. Not that we're going to need it right now, but a is 2, b is 13, and c is negative 24. So, concave up or down? Well, it's going to be concave up because a is positive. The y-intercept is our c value, which is negative 24. So that's our answer for number 4. Okay, let's try number 5. So are we in standard form? Do we have a number times x squared plus a number times x plus a number? Is that what this looks like? Well, no, not really, because, we have a number, but it's not times x squared, it's times x minus 1 squared. So we want to manipulate this again so that we're in standard form. And to do that, you can just, again, you can expand this by first rewriting the squared term as follows. We can write x minus 1 squared as x minus 1 times itself. That's what, when you square something, that's what that means. So we can rewrite it like that. And at this point, we can FOIL these things right here, because this is an understood multiplication sign, and we can just leave that negative 4 on the outside for now, and the plus 2 on the outside for now. All right, so let's go ahead and FOIL the x minus 1 times x minus 1. So FOIL, we have first is x times x, which is x squared. Outer is x times negative 1, which is negative 1x. Inner is negative 1 times x, which is negative x. And last is negative 1 times negative 1, which is positive 1. Okay? All right, combining like terms on the inside there and keeping that negative 4 chilling on the outside and the positive 2 on the outside. Negative x minus x is a negative 2x, so this becomes x squared negative 2x positive 1. Now at this point, you have this negative 4 being multiplied by all of this on the inside. We can distribute that guy to him, him, and him. All right, so we have negative 4 times x squared is negative 4x squared. Negative 4 times negative 2x is a positive 8x. A negative 4 times a positive 1 is a negative 4. And keep in mind, we still have that positive 2 on the outside. Okay? My last step here to simplify this completely is to combine those like constants. And negative 4 and a positive 2 makes a negative 2. So now we're in standard form. We have g of x is equal to negative 4x squared plus 8x minus 2. Okay? And we can now identify a, b, and c. So a is that number attached to x squared, which is negative 4. We have b is 8, and we have c is negative 2. Okay, so concave up or down? Well, a is negative 4. Since a is negative, this is concave down. And our y-intercept for number 5 is going to be c, which is negative 2. So our y-intercept is negative 2. Okay, so that's our answer for number 5. Okay, let's go ahead and try number 6. So Are we in standard form? Well, not quite, because we don't have an x squared, we just have a 3 minus x squared. So we need to do some manipulation to put this in standard form. So what I'm going to do is, just like with number 5, I'm going to expand 3 minus x squared into 3 minus x times 3 minus x, keeping the negative 5 as it is at the end and keeping the negative 2 in the front. So what I like to do is pull that 2 out and put 3 minus x times 3 minus x inside a set of brackets. Put the negative 5 on the outside like that. And now at this point I can go ahead and FOIL because I have multiplication understood here. So FOIL, we're going to do first 3 times 3 is 9. Okay. Outer, let's keep the 2 in the front, negative 5 in the back. Outer is going to be 3 times negative x, which is negative 3x. Inner is going to be 3 times negative x, which again is negative 3x. And last is going to be negative x times negative x, which is positive x squared. Okay? Now what I can do before I distribute is I can combine like terms on the inside. And that's just the negative 3x's can be combined here. So we have the 9 is going to stay where it is. Negative 3x minus 3x is a negative 6x. And then we have that plus x squared. So this is condensed to this. All right, PEMDAS, order of operations, says we need to complete multiplication before that subtraction. So multiplication is also known as, distributive property is like multiplication and addition combined. So we're going to multiply that 2 in there because that's what it's telling me to multiply 2 to each of these. So 2 times 9 is 18. 2 times negative 6x is negative 12x. And 2 times positive x squared is a positive 2x squared. That negative 5 is still hanging out in the back. And at this point, we can combine like terms. We can combine the 18 and the negative 5 to give me positive 13. So I get negative 12x plus 2x squared, and then positive 13 is that 18 and the negative 5. Okay, so at this point, are we in standard form? Almost. We just need to rearrange our term so that the x squared comes in the front, followed by the x term, followed by the 13. So let's just rearrange this, and now we're set. Now we can easily identify A, B, and C. So here A is 2, B is negative 12, and C is 13. And therefore this is concave up because A is positive, and the y-intercept is 13 because that's what C is. Okay, so that's how we do those. So that's the information that standard form gives us, is that it's concave up and that it's going to cross the y-axis at 13. Okay, that's the information that we know so far. Now I want to kind of hammer this point home that a quadratic function is just a function. It's a special type of function. And what I want to do is to ask you a question. And that question is, let's see, I'm going to erase some things so I can just do this off to the side. I really want to stress that this is the same thing that you did in intermediate algebra when you made T-charts. So I could ask you something like, is the point, I could say, is the point, let's see, 3, negative 5 on the graph? I could ask you that question. And what you could do is you could go to Desmos and plug in this thing and see if it lies on the graph. You could certainly do that. But remember how we do this algebraically is with a T-chart, okay? And so basically what the T-chart would say is that, we would have x and we would have 2 times 3 minus x squared minus 5. That's like our y, our output. It's our output of the function. And we're plugging in 3, okay, for x. And we want to see, do we get out negative 5 for y? Is that true? Well, let's see. We're plugging in 3 for x. Wherever we see an x, and we just see it in one spot, we get 2 times 3 minus 3 squared minus 5. 3 minus 3 is 0. 2 times 0 squared minus 5. 2 times 0 is 0 minus 5 is negative 5. So indeed, yes, this point is on the graph. What that means is, just as a reminder, when x is 3, y is equal to negative 5. And so, that's, and actually this isn't drawn to scale, but it's gonna be a point on this curve right here, and you could check other points too. So anyway, that's just a little side note that quadratic functions are functions. All right, so we talked about standard form. The next form I want to talk about is going to give us some new information. It's a new way of looking at the same thing that we just talked about. So we talked about standard form. Standard form gave us 2 pieces of information. The first piece is whether the graph is concave up or down. That's the first piece. The second piece is the y-intercept. Okay, that's the 2 things that standard form gave us. Now, this form is called factored form. It's basically you're dressing up your function to look a little bit differently, and it's gonna give you different information. Okay, so it's the same function, it's just disguised a little bit differently, and it's gonna tell us some different stuff about it. So factored form looks like this. Oops, let's erase that. Looks like this. Okay, looks different from standard form, right? This is what factored form looks like. And we have a, z1, and z2 are going to be numbers, okay? Now, a is also, in this case, going to tell us if it concaves up or down, but that's not really what we use factored form for. But a is the same a as the a in standard form. What is really cool about factored form is it's going to tell us where the graph crosses the x-axis. And this is going to have some physical implications. You're going to see why it's cool later on. Because, projectile motion, throwing things in the air, paths of objects in space are modeled with quadratic functions. And we're interested in knowing, how long does it take for an object to hit the ground or something like that. That's why where it crosses the x-axis is important. We're going to get more into that, though. Anyway, I'm rambling on about this, getting a little too excited, but bottom line, a, z1, and z2 are going to be numbers. A is the same as the a in standard form. It tells us if it's concave up or down, but this time z1 and z2 stand for zeros. Okay, that's where it crosses the x-axis. Okay, so zeros are x-intercepts. Zeros are the point where the graph crosses the x-axis. So like if we have something like this, let's say our quadratic function we put in Desmos looks like this, and maybe this is negative 4 and this is 2. Well, here the zeros would be x equals negative 4 and x equals 2. All right, so it's just where the graph crosses the x-axis. All right, so let's look at an example of a quadratic in factored form. I have one right here. Okay, so I put it in Desmos. It's y equals 2 times x minus 1, x plus 3. And so let's figure out what a, z1, and z2 are. Well, our factored form has minuses in the z1 and z2 spot. So, and maybe I'll just write it up here just so you guys can see the comparison in front of you. We have x minus z1 times x minus z2. All right, so what's a, z1, and z2? Well, a is clearly 2. It's that number in the front. And z1 can be directly replaced with 1 to make this exactly the same, right? X minus z1. Z1 has to be 1. Z2 is not 3, though, because of this minus sign in the original equation. Z2 actually has to be -3 for these to match up, right? Z2 has to be -3 for these to match up. So this is going to be -3. Okay, so it's kind of the opposite of what you see if you want to think about it like that. So this is my first 0. This is my first x-intercept. We can see it right here. Z1 equals 1. That's where it crosses the x-axis. And the other one is at -3, and we can see it right here. So that's the important information that our factored form gives us. Now, we can get other information by putting this factored form into standard form. So let's practice doing that. And we're going to get the same picture whether or not we input this into factored form or standard form. It's the same picture, but again, they're just dressed a little bit differently. One is dressed as in factored form, the other is dressed in standard form, but they're the same thing, right? They just give us different insights. All right, so let's convert this to standard form. So if we go from factored to standard, again, we're foiling it out. We're trying to expand it so that it's in the form y equal ax squared plus bx plus c. So what we start with is, let's see, we start with, let me write it out here, y equals 2 times x minus 1 times x plus 3. And we want to put this in standard, and so that just means expand, multiply, FOIL. So let's go ahead and FOIL these two things in the parentheses. We have x minus 1 times x plus 3. Let's go ahead and FOIL it out. So x times x is going to give us x squared. Outer x times positive 3 is going to give me a positive 3x. Inner negative 1 times x is negative 1x. And last but not least, negative 1 times positive 3 is a negative 3. So we just FOILed in the inside the bracket. That 2 is still going to be on the outside. And before I distribute that 2 in, what I like to do is I like to combine like terms first, just to get that out of the way. So positive 3x minus 1x is a positive 2x. So this becomes x squared positive 2x minus 3, okay? And now what I can do finally is distribute that 2 to everybody. That just means multiply. So we get y equals 2 times x squared is 2x squared. 2 times 2x is a positive 4x. And finally, 2 times negative 3 is a negative 6. Now we're in standard form. Okay, so we've just converted between forms. And maybe I wanted to know what the y-intercept was algebraically. And I can see it now in standard form. I see, oh, well, it's going to be negative 6. So (2x squared plus 4x minus 6). So if you were to put this in Desmos, it would be completely overlaid. It would be the same exact picture, but now we have a new insight. The new insight is this negative 6, and we can see it right here. So that's going to be our C. We also know that the other insight that we talked about was, it opens upward because A is 2, but A is also, we can also see A in factored form. So anywho, that was that example. Let's go ahead and try to find the zeros of the function algebraically. So when you are in factored form, it's really easy to find the zeros because what we want to do is, here's the idea. We want to set y, or f of x, or whatever it is, the output, equal to 0, and solve. And I want this to be clear of why we're doing this. Why are we setting y equal to 0? Well, because what we're looking for are these points right here. Zeros occur when y is equal to 0. That's why we're doing this, okay? So here, our y, we're going to set equal to 0, and we have 0 is equal to something times something else, and we want to, we want to solve for x. So I'm not going to like get too philosophical about this because you guys should think about it. Think about it on your own, but you were probably taught in high school to just set these things equal to 0, and you should think about why. Why are we setting them equal to 0? Like, why do we say, let's set x minus 3 equal to 0 and x plus 5 equal to 0? And the reason is because this is something times something else, and that equals 0. So either this equals 0, this equals 0, or they both equal 0, right? That's called the zero product property. So anyway, that's why we're doing that. If you have two numbers, and when you multiply the two numbers, you get 0, you can conclude, well, either one of the numbers is 0, or they could both be 0, right? Anyway, so we're going to set the factor x minus 3 equal to 0 and solve for x, and that's pretty easy. We just add 3 to both sides, get x equals 3, so that's my first 0. And you can call it z1 if you want to, but anyway, that's the first 0. We're just trying to find out what our x value is such that our y value becomes 0. And over here we do the same thing. X plus 5 equals 0. We're going to subtract 5 from both sides to get our second 0 is negative 5. So these are our zeros. You can think of these as our z1 and z2. If we were to look at this graphically, if we were to plug this into Desmos, you're going to get a picture that looks a little something like this. We know that it's concave up because this A is understood to be 1 in the front there. And it's going to cross that x-axis at negative 5 and 3. That's where our zeros are going to be. All right? Let's do the next one. So now that we know the process, this is going to be simple. This is acting like our y value. So we have 0 equals 3x minus 5, 2x plus 1. All we're going to do is set these factors, each of them equal to 0, and solve for x. That's how we're going to get our zeros. So 3x minus 5 equals 0, and 2x plus 1 equals 0. Let's go ahead and solve for x for each of these. I'm going to add 5 to get 3x equals 5, and then I'm going to divide by 3 to get x equals 5/3. So this thing is going to cross the x-axis at 5/3, and it's also going to cross the x-axis over here. If I solve for x, I'm going to subtract 1 and divide by 2 to get x is equal to negative 1/2. So it's going to cross the x-axis at both of those places, and what you should be doing throughout this lecture is verifying that I'm not lying and going on Desmos to check for yourself. Just put this equation in Desmos and make sure that this makes sense. All right, let's do this one, number 3. We have 5 minus x and 3 minus 2x. All right, so for step 1, set it equal to 0. So we're trying to figure out where y equals 0. Okay, sorry about that. I had a little brief interruption, a little cat fight. Anyway, we're going to set each of these things equal to 0. So we have 5 minus x equals 0. And we also have 3 minus 2x equals 0. And we're just going to solve for x in both cases. Now, what you can do in this first case, we can subtract 5 and divide by negative 1. But I think in this case it might be easiest to move the x over. That's perfectly legal. So if we want to undo negative x, we can add x to both sides. And when I do that, I get 5 left on the left side and x on the right. So we got our first 0, x equals 5. We can do the same thing over here. If I add 2x to both sides, I get 3 equals 2x, just adding 2x to both sides. Divide both sides by 2 to get x equals 3 over 2, or 1/2 if you like that. So these are my two zeros. This is where this quadratic is going to cross the x-axis. And I want you guys to notice that this is indeed in factored form. It's I mean, to technically be in factored form, the x value, or the coefficient of x, should be positive. But you can still do the same trick by setting each factor equal to 0. Okay, what about this one? So, no, this is not in factored form, so we cannot proceed. And, I remember teaching high school a while back, and what students would do is they would say, oh, well, I don't know, y equals 0, and let's see what we can do with this. And then they would do something weird and subtract 10 from both sides, and then they would kind of get stuck here. They would say, okay, well, I don't know what x would be here. So that's not the way to do it. That's not the way to do this. If you're in standard form, we can find zeros in two different ways that I'm going to talk about next, but we can't do the same thing that we did in factored form, and the reason is because the zero product property works really nicely. That idea of if we have two numbers multiplying to 0, one or both of those numbers has to be 0. But it's not going to work in standard form here. So we need a different method of attacking this beast. Okay, so how do we do it? So let's just summarize what we just talked about. If you're in factored form, finding zeros is easy. Just set each factor, basically stuff in parentheses, equal to 0, and solve for your variable. We did that in all of these examples here. We took everything in parentheses, set it equal to 0, and solve for our variable that way. Super straightforward if you're in factored form to find zeros. If you're not in factored form, what if you're in standard form, like in example 4? What do we do? How do we handle this? How do we find the zeros without using Desmos? Our first option is to factor, okay? So I'm going to show you how to do that first. And personally, this is a hard thing to teach because people teach it so differently. The way that I'm going to teach it is a more algorithmic kind of approach. I don't like to hammer too much on like the actual concept of factoring. It is interesting if you really get into the weeds of what factoring is, but I'm going to show you sort of a straightforward way to do this. Now, when would you factor? Well, when a is equal to 1, you can try to factor. That should be your first line of defense, because factoring is pretty easy to do, especially once you get used to it. So this is what we're going to do. This is how you factor. This is the algorithmic approach that I teach. You're going to find two numbers that multiply to C and at the same time add to B. And that's how you factor. That's what it is, okay? So what is our C? Our C is positive 10, and our B is 7 in this example up here. So what two numbers multiply to 10? All right, well, we have some options. We have 2 and 5. Let's look at our options. So we explore our options. We have positive 2 times positive 5. We also have negative 2 times negative 5. So that's option 1, option 2. We also have option 3, which is positive 10 times positive 1. and we can flip the order around as well. All right, so those are our options. Which of these three options are going to add to positive 7? Well, it has to be option 1. Positive 2 and positive 5 make a positive 7. Ding, ding, ding. So option 1 is our correct answer. A negative 2 plus a negative 5 is a negative 7, right? A positive 10 plus a positive 1 is a positive 11. So the only one that works is option 1. These two numbers 2 and 5, they multiply to 10, and at the same time they add to 7. All right? So we have x positive 2, x positive 5. And that's it. That's factored. You can check yourself by foiling. So you might be a little unsure. You might be saying, did I factor this right? Well, you can FOIL this back. So x times x is x squared. Outer x times positive 5 is positive 5x. Inner positive 2 times positive x is positive 2x. And finally, last is positive 2 times positive 5 is positive 10. Combine like terms to give a final answer of x squared plus 7x plus 10. And that is exactly what we started with right here. So you know that you factored it correctly if when you FOIL it back, you get what you started with. All right, so that's how you factor. And you can find the zeros at this point, okay? You can say, okay, well, now that I'm factored, did it ask to find the zeros? Well, I don't know. What was the question? Was it... So if the question said factor it, we would just leave it like this. If it said find the zeros, well then we would use our little method. We would say, okay, well, now that it's factored in factored form, I can set each independent factor equal to 0, right? Y equals 0, and solve for x. So over here, subtract 2, we get x equals negative 2 is our first 0. And our second 0, if we subtract 5 from both sides, we get x is negative 5. So these are the two zeros right here. And this is our factored form. All right, let's try to practice this. So, all right, so for number 1, we have which two numbers multiply to 2 yet add to 3. So, which two numbers multiply to 2, that's C, and add to positive 3. All right, so think about those two numbers. Think about your factors of 2. So the only factors of 2, we have negative 2, negative 1, and positive 2, positive 1. So it has to be positive 2, positive 1, right? So x plus 2, x plus 1. Again, you can check yourself by FOILing to see if you get this, but I'm not going to do that. So here it is factored. Now that we're in factored form, we can say y equals 0, and then we can set these individual factors equal to 0. So x plus 2 equals 0, x plus 1 equals 0, solve for x, x is equal to negative 2, solve for x, x is equal to negative 1. These are my zeros for number 1. That is where this parabola, this quadratic, is going to cross the x-axis at negative 2 and negative 1. Okay, let's try number 2. Now, here our variable is t. That's okay. And again, as I mentioned, you're going to see why I use t towards the end of this lecture. Let's go ahead and factor. So here, the question is, which two numbers multiply to negative 6, that's C, and add to, well, there's no number written in front of that variable, so it's understood to be 1. That's our B value. Positive 1. So think in your head, factors of negative 6. Which two numbers multiply to negative 6? It's negative 3, positive 2, but negative 3 plus 2 is negative 1. It's not positive 1. So you need to do a switcheroo there. So the correct answer here, and again, this is trial and error. This is just, thinking about factors of negative 6 and seeing if those factors add to positive 1. And what I just said was, negative 3 and positive 2 do multiply to negative 6. But when you add negative 3, positive 2, you get negative 1, which is not positive 1. So instead, we should do a positive 3 and a negative 2. right? Because positive 3 plus negative 2 is positive 1, not negative 1. So we have x plus 3, x minus 2. And again, well, actually t, sorry. This should be t plus 3, t minus 2. And again, check yourself just to make sure you can FOIL it back, see if you get this back. This is factored. Now let's go ahead and set these guys equal to 0. So 0 equals t plus 3. And we also have 0 equals t minus 2. Solve for t to get t equals negative 3. And I'm kind of going out of order here just to make room on the page. And over here, when we add 2 to both sides, we get t equals 2. So these are my zeros. This is where it crosses the x-axis. All right, let's try number 3. Okay, so what two numbers multiply to negative 40 but add to 3? Okay, which two numbers? You always want to think about the numbers that are being multiplied first. Which two numbers multiply to negative 40 and add to positive 3? Let's see. Well, negative 8 and positive 5 make a negative 3. So a positive 8 and a negative 5 make positive 3. So our answer here is x positive 8, x minus 5, right? Positive 8, negative 5 make a positive 3. And positive 8 times negative 5 multiplies to negative 40. All right, so that was our first step. We're in factored form. Now we can set the individual factors equal to 0. So x plus 8 equals 0 and x minus 5 equals 0. So we get x equals negative 8 and x equals 5. So those are our x-intercepts, aka our zeros, aka where it crosses the x-axis. Again, check Desmos to verify that that makes sense to you. Okay, here we have an issue. The issue is that my a is not 1, so we can't go on and start factoring this unless you know of a better way to do it. However, what you should recognize is that these three terms all have a number that can be divided out. They all have a common divisor. What's the biggest number that divides 2, negative 14, and positive 24? What's the biggest number that divides those three? Is 2, right? 2 will divide all of these. So what we can do is we can pull a 2 out. We can basically divide it out, right? We can kind of do a little mini factor, mini factoring going on. So if we divide out the 2 here, we're just left with w squared, right? That makes sense. When we distribute that back, we get 2w squared. When I divide the 2 here, I get a negative 7w. When I divide the 2 here, I get a positive 12. And just like with factoring that we did up above, if we distribute that 2 in there, we should get exactly what we started with. So that's how you can check to see if it's right. And now we're in a good position because this guy is in standard form. We have A is 1, which we wanted, B is negative 7, and C is 12. So we can factor this thing, okay? And so what you're asking yourself right here is, which two numbers multiply to what's your C value? Your C value is 12. And add what's your B value? Your B value is negative 7. Right? And we have to be in this form to do this trick. We have to have A being 1 to do this. That's what we couldn't do it here. We had to pull out that 2. Okay, so let's go ahead and answer this. Which two numbers multiply to 12 and add to negative 7? I'm thinking of 4 and 3 make 7. So how about negative 4 and negative 3? So this becomes, the 2 is going to stay there. And then we have w negative 4, w negative 3. Negative 4 and negative 3 multiply to give us positive 12. And if I do negative 4 plus negative 3, I get negative 7. So we know that we made the right choice there. Now we're in factored form. See, now we have an a that's not 1. We have a is 2, but we can still employ the same strategy. We set these factors equal to 0. Not this one, though, right? Because, first, if we set y equal to 0, which is the first step in doing this, we get 0 equals 2 times w minus 4 times w minus 3. And would it make sense to say 2 equals 0? Well, no, that's absurd. 2 does not equal 0 here. So we set w minus 4 equals 0 and w minus 3 equals 0. The 2 can go somewhere. We don't need it. It doesn't make sense. So the only things that can be 0 here is w minus 4, w minus 3. Adding 4 to both sides, we get our first 0 is w is 4. Our second 0 is w is 3. So these are going to be our intercepts where it crosses that horizontal axis. In this case, it's not the x-axis, it's the w-axis, but all the same. What about number 5? Okay, we can't factor it right off the bat because this leading coefficient is not 1. However, check it out. All of these terms have a common factor, a common, common factor, common divisor. What's the biggest number that can divide all of these evenly? Well, that's going to be 5. Now I can pull a 5 out. Right, and again, I use the same trick. I just divided 5x squared by 5, negative 20 by 5, and negative 25 by 5 to get these things down here. That's a 1 in front of the x squared. And now, at this point, I can factor this using our trick. Which numbers multiply to negative 5, yet add to negative 4? How about negative 5, positive 1? Negative 5, positive 1. X minus 5, x plus 1. Okay, and you can FOIL it out to check. All right, now that it's all factored, we can set the factors equal to 0, solve for x. So we get x minus 5 equals 0, x plus 1 equals 0. Therefore, x equals 5 and x equals negative 1. And those are our x-intercepts, or the place where the function is going to cross the x-axis. Just a little memory, or I don't know. This is in standard form, so this also tells us that our y-intercept is negative 25. Nice little tidbit there. All right, let's do one more. So we are in standard form, so the only thing we know is that it's concave up because of this a value, and it crosses the y-axis at 24. But we're interested in the zeros. We're interested in where it crosses the x-axis, or in this case, the m-axis. That's our independent variable. What can I do? Well, I can pull out a 3, certainly. All 3 of these can be divided by 3. So let's go ahead and pull out the 3. When I pull out the 3, 3m squared divided by 3 is 1m squared. Negative 18 divided by 3 is negative 6m. 24 divided by 3 is 8. All right, now I can factor this piece right here. What two numbers multiply to 8 yet add to negative 6? That's going to be a negative 4 and a negative 2. All right, so this becomes m minus 4, m minus 2, right? Negative 4 and a negative 2 make negative 6 when we add them, and they multiply to positive 8. All right, so now instead of the q of m, that's our output, we're just going to put 0. 0 equals 3 times m minus 4 times m minus 2. Set the m minus 4 equal to 0 as well as the m minus 2. And we get that our zeros are 4 and 2. So that is where this thing is going to cross the x-axis. And you should check Desmos again, just to verify. Okay, so we took care of that, factoring. Sometimes you can't factor, or sometimes, dare I say it, you may not want to factor. There's another option for you, and that is the quadratic formula. Okay, it's this. That's basically what it is. Okay, so you're in standard form. All right, we're in standard form. We love it. It's equal to 0. Great. Once that happens, we can use this lovely formula right here. I'm not going to prove how you get the formula. If you're interested, there's plenty of YouTube videos on it, or we can talk in office hours. It's a pretty cute little proof. But anyway, let's go ahead and get going. I don't know how to factor this. How about you? Yeah, we can't take a 6 out of this middle term, so we can't do the little trick that we did in the last problem. We can't do that here because 17 is not divisible by 6. So when this happens, you gotta bring out the big gun, and that's the quadratic formula. So all we have to do is identify A, B, and C, because that's all that's used in the formula. And this formula spits out the zeros. X, this is the zeros. And we have 2 zeros. We have a plus and a minus here, and I'm going to show you how that goes. All right, so first of all, identify A, B, and C. That's the first step. So what's A, what's B, and what's C? So in this case, A is attached to x squared, so that's 6. B is attached to x, that's negative 17. And C is that constant at the end, which is just 12. So now we just plug everything in. So we have the zeros, which is x, that's my zeros, equals negative b. So we have negative is already there in the formula, and then we input b. I would put parentheses when you're first doing this just to not get confused. So in place of b, I'm putting parentheses what the number for b is. Okay? Plus or minus, that's what the formula says, square root of b. Again, I'm putting parentheses to say I'm inputting something for b. Minus 4, I'm inputting a and c. So I'm inputting a 6 and I'm inputting a 12. And this is all going to be over 2 times a. All right. Now, this is pretty ugly, but we can clean it up. No problem here. So we get these double negatives multiplied make a positive 17. That's the first piece of ugliness we can... I mean, I guess it's not ugly, but it just looks more complicated than it is. The second piece of information that we can simplify is this negative 17 squared. Let's put that in the calculator. What's negative 17 squared? 289. I'm just going to put that there. All right. Now, actually, let me put that. Just circle that. Okay. And now, this is where students get confused sometimes. Not all the time. But don't forget that this negative is attached to the 4, okay? We have negative 4 times 6 times 12. Negative 4 times 6 times 12. Put in the calculator. Negative 4 times 6 times 12. I get negative 288, and that's exactly how I'm going to write it. On the bottom, 2 times 6, 12. Now, under the radical, 289 minus 288, we all know, I think, that that's 1. So I'm going to replace that with 1. And finally, square root of 1 is just 1. Put it in the calculator. Square root of 1 is 1. So we get x is equal to 17 plus or minus 1 over 12. So two answers here. So the first answer is 17 plus 1 over 12, right? That's the top there. The second answer is 17 minus 1 over 12. Okay, two answers, 2 zeros here. So first one, we get 18 over 12. Oh my gosh, my brain doesn't like arithmetic. Let's see, if we simplify it out, divide by 6, we're gonna get, guys, I can't do, it's funny, I have family and friends that think that you know, because I'm a PhD student in math and I've been a math teacher for basically 10 years. People think I can do arithmetic really well, but I really can't. It takes me a while. So, let's see. 18 divided by 6 is 3. 12 divided by 6 is 2. All right, we got it. So first 0 is 3 over 2, aka 1/2, or 1.5, I should say. This guy is 16 over 12. So x equals 16 over 12. Divide top and bottom by 4 to give me 4 over 3. So these are my two zeros. The quadratic formula does a great job of giving us those. And by the way, it works for any quadratic equation, even the ones that can be factored. It works for any of them. So let's do another example. All right, so quadratic formula, maybe I should actually put it in here in this slide just so we have it. All right, first things first, are we in standard form? Yes, we are. What's A, what's B, what's C? Well, A is going to be 1. It's understood to be 1 there. B is 16, and C is 7. And let's just plug in these guys into our handy-dandy formula here. So negative B, I'm inputting a 16. Negative B plus or minus square root, I'm inputting a 16 again. Squared minus 4 times 1 times 7 all over 2 times 1. Okay, anything I input, I put it in parentheses. All right, cool. So let's go ahead and clean it up. This negative 16, we can just get rid of the parentheses there. 16 squared, I'm going to put it in my calculator to get 256. All right, now don't forget about that negative sign. Negative 4 times positive 1 times positive 7 is going to be a negative 28. All right. And that's all over 2 times 1 is 2. So 256 minus 28, I'm going to get 228. So this is going to give us x equals negative 16 plus or minus root 228 all over 2. You can simplify this if you want, but I don't think I'm going to focus on that right in this video about simplifying radicals. You can just leave it like this because this isn't a perfect square. So you have two answers, and they're weird answers. They're decimals. They're irrational numbers, but that's okay. The first place it's going to cross the x-axis is at negative 16 plus root 228 all over 2. And the second place it's going to cross the x-axis is negative 16 minus root 228 all divided by 2. Now, if you were to put these in Desmos or your graphing calculator or whatever, you're going to get a decimal, okay? You're going to get a decimal approximation of where this curve, where this quadratic, this seemingly innocent-looking quadratic, is going to cross the x-axis. All right, what about this? Well, you might be saying, wait a minute, this doesn't look like the other ones. Yeah, it doesn't. We want to, first and foremost, make sure that we have everything set equal to 0. It has to be in this form for you to factor and for you to use a quadratic formula in order to find your zeros. So let's go ahead and make sure this is in this format first. So we want to make sure that we have 0 on one side by itself. So what I'm going to do is I'm going to move everything over to the left side simply by subtracting, just using the laws of math, the laws of algebra to keep this equation balanced. So I'm going to subtract over the 7x, and I'm going to do this step by step just to make sure everyone's following. All right, when I do that, I get this, and now I'm going to subtract the 4 over. Right, from both sides. When I subtract the 4 on the right, I get 0, and now I'm in this form. I'm in ax squared plus bx plus c equals 0. So here we have a is 9, b is negative 7, and c is negative 4. And we can just plug this stuff into our quadratic formula at this point. So our zeros are going to equal negative b plus or minus the square root of b squared minus 4 times a times c. And this is all going to be divided by 2 times a. All right, so let's clean it up. So we get let's see. Well, this double negative becomes a positive 7. So we have 7 plus or minus square root of negative 7 squared is 49. Then we have negative 4 times positive 9 times negative 4. What's that going to give us? Let's see. Times positive 144. Okay, so let's see what that gives us. I get 193, which is not a perfect square. So I'm just going to leave it. I'm going to say x is equal to 7 plus or minus root 193 all over 18. So 2 answers. Again, funky looking decimals, but it's all good. We have 7 plus root 193 over 18. And the second place that's going to cross the x-axis is at 7 minus the square root of 193 all over 18. So these are going to be my zeros here, found by the good old quadratic formula, MVP. Never going to let you down. So if you ever can't factor, or if you don't feel like it, you can always use the quadratic formula. Now, what if you had something weird like this? What if you had, 2x squared equals 0? Well, you could still use the quadratic formula. It's going to be kind of boring, but you can use it because here a is 2, b is not there, so it's 0, and c is also gone, so c is 0, and you're gonna see that that it's gonna cross the x-axis at x equals 0. And you can confirm with Desmos that this works, confirm with the quadratic formula that you get the right answer. Okay, so given what we know, let's give a formula for this quadratic function. So we have 2 tools at our disposal. We have standard form and we have factored form so far. Now, when you're trying to give a formula for a quadratic function, you don't want to use standard form because there are too many variables to worry about. You're not going to be able to get what you need. So we're going to use factored form. And so remember, we have factored form is going to be of the form y equals a times x minus the first 0 times x minus the second 0. And this picture is going to give us all the information that we need. In order to write a formula in factored form, we need numbers for a, z1, and z2. And the picture is going to give us something for free. Or it's going to give us 2 things for free. It's going to give us z1 and z2. So the z1 and z2 are the zeros. That's where it crosses the x-axis. So it doesn't matter which one you call z1. I usually just do the leftmost one. So z1 we can see right off the bat is negative 2. And z2 is, let's see, this is going up by halves. So this is 1, 2, and this is going to be 3. So this is z2 equals 3. All right, so we got 2 pieces of information. So we know that z1 is negative 2 and z2 is 3. And the question is, how do we find a? Well, we find a by choosing another point on this curve and subbing it in. So subbing in an x comma y value to get a. Because if we have all numbers in one variable, we can get it. So just reiterating what we just found, I'm going to just plug in what we have so far. We have z1 is negative 2, so we have negative 2. And then z2 is 3, so we have this so far. And what I'm going to do right off the bat is condense those double negatives to a positive so that we can work with this a little bit easier. Okay, and we need to figure out what a is. That's what our mission is. So, how do we do it? Well, we pick a point on the curve. This one looks easy. This is an easy point, but you could have easily have chosen this point. That's a nice point too. There's a lot of different points you could choose, but I'm going to choose a y-intercept just because it's the first one I saw. So what is the ordered pair associated with this? Well, x is 0 and y is 6. It's the y-intercept. So if I sub in, and maybe I'll do this in a different color, how about purple? If I sub in x is 0, y is 6, and it has to be like the corresponding y to an x value. You know what I mean? Like, I can't just say, oh, well, y is 6, but look, x is 2 here. No. It has to be the one that, like, the x that corresponds with a given y, right? So the x that corresponds with y being 6 is x equals 0. So wherever I see an x, I'm going to plug in a 0. Wherever I see an x, I'm going to plug in a 0. So we have 0 plus 2, and then we have 0 minus 3. Okay, let's go ahead and simplify it out. So we have 6 on the left times a. All right, so 0 plus 2 is 2. So this is just times 2. 0 minus 3 is minus 3. And then I can simplify even further. 2 times negative 3 is negative 6. So this is 6 equals a times negative 6. And now this is super easy because we can figure out what a is by dividing both sides by negative 6. Right? 6 divided by negative 6 is negative 1, so a is equal to negative 1. And we have our answer. Our answer is y, right? I'm using what we found up here. Y is equal to negative 1 times x plus 2 times x minus 3, and that is our formula for this guy. And it makes sense that a is negative because we have a frowny face, right? So that is our formula, and again, verify with Desmos just to double check and convince yourself. All right, let's try another one. Write a formula for the quadratic function whose graph has a y-intercept of y equals 7 and x-intercepts at x equals 1 and 8. Since we're given x-intercepts, aka zeros, it makes sense to use factored form here. Again, so we have a times x minus z1 times x minus z2, and we need to figure out again what a is. That's kind of like our trouble spot, is figuring out what a is so that we can write the formula. And remember, when I say write a formula, what does a formula actually do for us? It leaves x and y alone, right? Because the whole point of a formula is to put in some stuff for x, whatever we want, and to get out some stuff for y. So we want to leave the machine we want the machine to have input variables and output variables. All right. So the x-intercepts are z1 and z2. So z1 we can say is 1 and z2 is 8. It really doesn't matter which one's which. But anyway, so y equals a times x minus 1, x minus 8. All right, so far so good. Now we're going to use the same trick that we employed in the previous slide to get a. Now, the y-intercept is a point in disguise. The y-intercept is secretly x equals 0, y equals 7. So that's what we're going to do, is we're going to sub in y is 7 and x is 0. That's a point on this curve. So we have y is 7, so I'm going to sub in 7 for y. We're trying to figure out what a is, and the corresponding x value that goes with 7 is x equals 0. So we have a times 0 minus 1 times 0 minus 8, and let's go ahead and clean this up. So we get 7 equals a times negative 1 times negative 8, which is negative 1 times negative 8 is positive 8. So we get a times positive 8. Divide both sides by 8 to get a is equal to 7 over 8. Everything we need now we have a, and so I'll sub that in there to get my final answer of 7 over 8 times x minus 1 times x minus 8. We do expect this parabola, when we put this in Desmos, we expect it to open up like this because this a is positive. Doesn't matter that it's a fraction. It's positive, it's going to open up. And we also expect the graph to cross the x-axis at 1 and an 8. Okay. All right, let's try another one. The zeros of a quadratic function are at 3 and negative 2. and the quadratic passes through a point negative 1, 6. So not the y-intercept, but we still have an x comma y. We want to find the factored and the standard form of the equation. Again, when you're trying to find these equations, always start by putting it in factored form, because you're gonna, if you do this just by like trial and error, like if you forget about this when you're doing your homework, you're gonna see that with standard form, there's too many variables to solve. Anyway, let's go ahead and put this in factored form. So factored form, we have a times x minus z1 times x minus z2, and right off the bat, we're given z1 and z2. Yes, they do say it's x, but the context clue here is 0. So when you see 0 and they tell you what the zeros are, you need to think z1 and z2. I know it can get confusing because you see an x there, but they, so all I can say is I'm sorry if it confuses you, but the sentence itself is saying the zeros are this and this, so you want to replace them in for the zeros. Okay, so we have y equals a times x minus, first 0 is 3, second 0 is negative 2. And those double negatives are going to become a positive, so I'm going to just replace that just for the sake of simplicity. Okay, now the mysterious a has arrived, okay? We need to figure out what that is using this point that they give us. They tell us from this point that x is negative 1, and the corresponding y is 6, and that's what we're going to plug in for x and y here. So y is 6, so we have 6 equals a, which we're trying to find, times x is negative 1, and so wherever I see an x, I'm going to plug in a negative 1, right? And let's go ahead and simplify this out. Negative 1 minus 3 is a negative 4, and a negative 1 plus 2 is a positive 1. Okay, negative 4 times 1 is negative 4, so we have a times negative 4 equals 6. Divide both sides by negative 4 to give me 6 over negative 4, which reduces by 2. That's going to be negative 3 halves, or negative 1.5. So that's our a. So our formula in factored form is going to be negative 3 over 2 times, what did I say up here? X minus 3, x plus 2. Okay, so this is in factored. And I'm going to do the standard pretty quickly, just because we've done so many examples. So let's go ahead and do that. I'm going to FOIL this out. So I get x squared plus 2x minus 3x minus 6. And that's all being multiplied by that negative 3 over 2. And if I combine like terms, I get x squared, negative x minus 6. And I'll go ahead and multiply that negative 3 over 2 in there. So I get y equals negative 3 over 2 x squared plus 3 over 2x plus 9. How did I get that? Negative 3 over 2 times negative 6 over 1 is positive 18 over 2, which reduces to 9. Okay, so this is in standard form. So we can see A, B, and C. All right, let's do some real-world problems. Okay, so a high diver jumps off a 10-meter platform. We're thinking 10 meter in height. I know it's kind of worded weirdly, but 10 meter in height platform. For t seconds after the diver leaves the platform until she hits the water, her height in meters above the water is given by this function. Okay, so her height depends on time, right? That's why we use t typically with quadratics, because distance depends on time. All right, so interpret the intercepts of this function as well as the domain and range. So first of all, let's think about what our y-intercept is. Let's interpret this in a real-world context. Well, our y-intercept, this is in standard form. We can see a is negative 4.9, b is 8, and c is 10. And so C, right off the bat, you can see it's 10. So the y-intercept is 10. And the context of this, the y-intercept occurs when x, or when t in this case, is 0. Okay, so this occurs when t equals 0. And so, what we can conclude here is that that's the starting height of the diver, right? The 10-meter platform. This is the starting height of the diver. So that's the real world implication here of the y-intercept. What about the x-intercepts, or in this case, the t-intercepts, right? Because our variable just shifted to t, but we're thinking of it like we usually do with x. Well, how do we figure this out? How do we figure out what the intercepts are? Well, we have to set this equal to 0, right? Because the t-intercepts happen when our output is 0, just like, when we were trying to find the zeros, we set y equal to 0. It's the same thing here. We're saying, okay, well, what's t when y, or h of t, is 0? So when h of t is 0, what is t? And right off the bat, you can see we're in standard form. We cannot factor this. I wouldn't know how to factor this. I mean, we have a decimal for, in the front. So forget about factoring. We need to use the quadratic formula. Or we can cheat, and that's what I'm going to do here because I don't feel like using a quadratic formula. So let's do a little cheat, a little sneak. We're going to put this in Desmos. So and instead of t, I'm going to use x because that's the letter that Desmos likes. So let's go ahead and put it in Desmos. Okay, all right, there it is. So let's zoom in a little bit, just kind of pinch. All right, so let's look at the intercepts, the t-intercepts, aka the x-intercepts. Well, we have a negative t. We have negative 0.829, and we're going to throw that out of the window because that doesn't make sense in our real-world context. How can time be negative? What about this one? So this is 2.462. So we have this intercept, and I'm going to write it down, 2.462. Let's write it down here. So we have, and what was the other one? The other one was the weird negative 0.829. So we chuck this out the window. Doesn't make sense. Time can't be negative. This one does make sense though. And what does it mean? What does it mean? Well, what it means is this is the time when the diver hits the water, when the height is 0, right? So this is the time when diver hits the water. Okay, so that's going to be this time right here. Now, the domain and range, it says interpret the domain and range. And so you can interpret it, you can actually interpret this question in two different ways because it's a little vague. You can say, okay, well, I'm going to interpret this just by looking at the function, or you can do something a little bit more sensible and interpret this in terms of the real world representation. So in terms of the real world domain and range, let's say that I'm thinking of this as just a strictly real world problem. And I want to know how far to the left does this thing go to how far to the right. Well, if we're thinking real world, then we're going to cut off everything where time is negative, right? We're going to cut off all of that. So the domain is going to start at t equals 0 because that's what makes sense in the real world. And I can't really... I wish I could show you this a little bit. Well, yeah, I guess I can show you. We're going to restrict the range to when height isn't negative. Height's negative below the x-axis. So we're going to restrict the range to right here. Okay, so this is where it makes sense in the real world. So what's the domain? What's the range? Well, the range, the lowest this thing is going to be is at a height of 0, right? That's the lowest this thing is going to be. And the highest it's going to be is at a height of 13.265. All right, so let's write that down. So the range, we're going to go from a height of 0, and now I forgot it already. What was it? 13.265. Okay, yeah. Got it. All right. 13.265. So that's a range. And the domain, how far left to how far right? Well, the time starts at time equals 0, and she's going to hit the water at time equals 2.462. You can also see it on the graph right here. And so that's going to be our domain. So we're going from 0 to 2.462. Okay, so that's the domain and the range. So the domain tells us when she starts to dive to when she hits the water. And the range is going to tell us the minimum to maximum height she reaches. So the minimum height is going to be 0. And, right, that's when she hits the water. And the maximum height is going to be 13.265. Okay. And now real world. Where is it increasing and where is it decreasing? So remember, when we talk about increasing and decreasing, we talk about the x interval, the time interval. So we're increasing from time equals what to what? Well, we're going to be, and remember, we're talking real world, so we're restricting our picture to just this piece. Where is it increasing? Well, it's increasing from time equals 0 all the way to this top part, to time equals 0.816. So increasing from, and let's put it in parentheses to be technical with it, x equals 0 to 0.816. Why is it parentheses and not brackets? Well, that's a deep question. It's, we're not technically increasing on 0. We're increasing after 0, like really, really close to 0, but not actually, we're not increasing on 0, because there's some movement associated here with the word increasing and decreasing. Anyway, now we're decreasing, so she's falling from 0.816 all the way to time equals 2.462. And, what's the real world interpretation? Rising in height is where it's increasing. That diver is rising in height. And where it's decreasing, she's falling. She's going towards the water. All right, so that was our first real world example. Now let's talk a little bit about another one. We're going to be talking about velocity. Now, if you take Calculus 1, you're going to talk a lot about velocity, especially if you take me. I like to talk about velocity, acceleration, stuff like that. So velocity is, in short, it's just speed with a direction. Okay, so, like when you talk about speed, when you talk about going 80 miles an hour on the interstate, we don't know where you're going. We don't know if you're going towards El Paso or if you're going towards Tucson. We're not really sure what direction you're going in. When you talk about velocity, you associate a direction to that speed. So you say, okay, I'm going 80 miles east, or I'm going 80 miles west. That's kind of the difference. We'll get more into that, as time goes on. But anyway, here's our velocity function. Okay, v of t equals t squared minus 4t plus 4. It's going to represent the velocity after t seconds of an object in meters per second. What is the object's initial velocity? Well, that occurs when the time is 0. Okay, initial velocity occurs when the time is 0. So all we're going to do is plug in 0 into this function and see what our output is. So we're plugging it in for t, and we get 0 squared minus 4 times 0 plus 4. So we get 4 meters per second is our initial velocity. When is the object not moving? Keyword when. What are we looking for? What is a when? What kind of word is when? Time, right? We're looking for time. At what time is the object not moving? Well, not moving corresponds to a velocity of 0, right? So instead of v of t, instead of velocity, we're going to replace that with 0, and we're going to solve for that corresponding, or those corresponding t values. Okay, so we get this, and we need to solve for t. So we're in standard form, which means that we can factor or use the quadratic formula. It might be easier to factor here because your a value is 1. Can I factor this? Yeah. What two numbers multiply to 4? Wait, no. Yes, we can. What two numbers multiply to positive 4 yet add to negative 4? That's going to be negative 2 and negative 2. Okay, so we have, this is t minus 2, t minus 2. Okay, each of these factors is the same, so if I set just one of them equal to 0, which is sufficient, we get t equals 2. So this is at 2 seconds, the object is not moving. Okay. Now let's go ahead and interpret v of 4. What does that mean? We're inputting 4 into our velocity function for t. So v of 4, if I plug in 4 anywhere I see a t into my function up here, I get 4 squared minus 4 times 4 plus 4. Lots of 4s going on. We get 16 minus 16 plus 4. This is 4. So what does v of 4 mean? Well, this is the velocity when time is equal to 4 seconds. That's what we're inputting 4 seconds, and the output is velocity. So that's going to be in meters per second. So velocity when t equals 4 seconds, and this is going to be 4 meters per second. Okay. All right, let's do one final example here. A water balloon is launched straight up. The balloon's flight is modeled by this height function right here. And h of t represents the height of the water balloon after t seconds. And I took the liberty of putting this function in Desmos so that we can get a little picture here. It says at what height did the water balloon get launched from? So that occurs when t equals 0, right? So we can look at this algebraically, or we can look at it graphically. But when t equals 0, that corresponds to time being 0. We get negative 16 times 0 squared plus 192 times 0. We're assuming that the water bottle has a negligible height. That's the idea here. So simplifying this, we get 0. Okay, so this is a height of 0. Well, I didn't give units for height. I should have, but anyway. 0 is the height. When did it reach its maximum height? Well, pictorially we can see where it hits the maximum height. That's right here. Okay, that's at 6 seconds. That's at 6 seconds is where it reaches its maximum height. Now let's prove this algebraically. So you're going to have to do that in your homework. Algebraically, I think you're going to have to do it in your homework. Don't quote me on that. algebraically, it's going to well, no, we're not going to get to that in this lecture. I'm sorry, I'm confused with our next lecture on vertex form. Forget about it. Okay, so it doesn't say algebraically, just look at the graph. When did it reach its maximum height? At 6 seconds, it reached a max height of 576. Okay. When did it hit the ground? Now we can show this algebraically and graphically. So when did it hit the ground? Well, graphically, that's here, right? That's when it hits the ground. That has a height of 0. So it hits the ground at 12 seconds. Now let's prove this algebraically. So algebraically, when it hits the ground is when the height is 0. So we plug 0 in for h of t and solve for t. Okay, so we get 0 equals, let's see, negative 16t squared plus 192t. Now, can you use the quadratic formula? Certainly, you can. You can say, oh, A is negative 16, B is 192, C is 0. Do you have to use the quadratic formula? No, you do not. Why? Because there's no C, and what you can do is you can pull out a greatest common factor from these two terms, a greatest common factor of t. Pull out a t, and actually, let's see, does 16 go into 192? Yeah, it does. Sorry, you can actually pull out more than t. You can pull out a negative 16t, right? If I divide this by negative 16t, what's left is t. If I divide this by negative 16t, well, 192 divided by negative 16 is, so it's going to be negative 12. Right. Okay. Cool. All right, so it's all factored up, and now we can set each individual factor equal to 0. So if I set this guy equal to 0, negative 16t equals 0. That's a factor, even though it's not in parentheses. Divide both sides by negative 16 and get t equals 0. Now it doesn't hit the ground there. It's launched from the ground that corresponds to that little intercept right there. So we don't really need to include this in our answer because it doesn't hit the ground there. What it's talking about is this guy right here. And I get that guy by setting this other factor equal to 0 and getting t equals 12. So that's how we find that algebraically. What was its height at 9 seconds? So here we're being told that t equals 9, find h of 9. That's what we're trying to figure out. So when t equals 9, what's h of 9? Well, so we just take our function h of t equals negative 16t squared plus 192t, and we're going to plug in 9 anywhere we see a t. Okay, let's do the computation. All right, so I'm getting 432. So this is going to be our answer for part D.